Hey guys, I want to apologize for not being here today. I created this little video so that you guys won't fall behind. I realized that some of you may have had some trouble with the homework on constraints on trig functions and evaluating the trig functions. So if you struggled with the homework and weren't able to come in for Bulldog Block, come and see me on Monday morning and I'll go over any questions you might have and fix any errors that you made. In the meantime, we're going to talk about graphing trig functions today, specifically the sine and the cosine function. And so I'm going to get you started. We'll spend today looking at some vertical transformations of the graph, and then next week we'll start looking at some horizontal transformations, similar to the kinds of transformations we did at the beginning of the year when we were shifting and reflecting and dilating graphs. Notice we've got our unit circle. Now, this is a different format of the unit circle. I wanted to squeeze it all onto one page. But I want to take a look, for example, at the first function that we're going to be graphing is the sine function. And basically what I'm going to do is I'm going to take the sine of theta and I'm actually going to set it equal to f of x, or f of theta, I guess in this case. We're going to be talking about f of theta. Let me fix that so it's proper. F of theta. Okay, and that's just function notation, where theta is my input. So theta is my input, that's going to correspond to my domain, and we're used to using, the value of x as our input, but now since we're dealing with a unit circle and we're dealing with angles in the unit circle, I'm going to call it theta. Sometimes you'll see it as the sine of x. Don't get confused. All it's talking about is the input value being an angle on the unit circle. And then our sine value of whatever theta is going to be our output. So the output is essentially all of the y values that correspond to the different theta measure. So for example, if theta is 0, and I'll just go ahead and talk in terms of radians. If theta is 0, the value of y is 0. If theta is pi over 6, the value of y is 1/2, and so that would be the sine. If theta is pi over 4, then the value of y is square root of 2 over 2, and so forth. And notice that as I'm going around the y values, I'm going from 0 to 1/2. The square root of 2 over 2 is a little bit bigger than that. Square root of 3 over 2 is a little bit bigger than that. And then I get all the way up to 1. And then as I continue around my unit circle, I start to go back down. The square root of 3 over 2, the square root of 2 over 2, 1/2, and 0. So my value for y gets larger and then it gets smaller. And then notice when I cross over pi, my values of y start to become negative and they approach -1. And then they start to increase again to 0. And as we've seen before, I can do more than one rotation around the unit circle. If I keep going, notice the values of y start to increase. They increase, and then they start to decrease to 0. Then they start to decrease a little bit more to -1, and then they increase to 0. And then they increase to 1, back down to 0, back down to -1, back up to 0. And so what we're going to do is essentially just map out those values on a coordinate plane. And so if you take a look at your first page in the classwork, we're looking at the value of when y. And so instead of using function notation, I'm just calling it y. So we're going to be graphing y is equal to the sine of theta. And so what I'd like you to do, in just a few minutes, I'm going to have you pause this video, and what I'd like you to do is rewrite each of the values of the sine of theta into this table format. So if you look back at your unit circle, where the value of theta is 0, if you look at the sine value, so this is where theta is 0, or 0 radians, the sine value is 0. And so I'm going to put that in my table. If I'm trying to evaluate pi over 6, if I go back to my unit circle, at pi over 6, the value of y is 1/2. And so what I'm going to recommend is that you write all of these values as decimals. Well, we know that 1/2 is just 0.5. When you get to pi over 4, however, with pi over 4, you have the square root of 2 over 2. And so what I'm going to ask you to do is actually evaluate the square root of 2 over 2. And so if we calculate the square root of 2, now be careful, before I divide by 2, I need to close the parentheses and divide by 2. And I find that the square root of 2 over 2 is equivalent to about 0.707. And actually, let me just write that up here because that's a really common one that we're going to be coming across. At pi over 3, we have the square root of 3 over 2. And so if I find the square root of 3 and divide by 2, we have 0.866. So the square root of 3 over 2, that's another popular one that we're going to be coming across over and over again. At pi over 2, I know that the value of sine is 1. And then it goes back down, 0.866, 0.707, zero point 0.5, and 0. What I'd like you to do is pause this video, complete the table, and then I'd actually like you to plot the points on the graph below. Now, one of the things you might notice on the x-axis, which actually I should have referred to this as the theta axis because that's our input, one of the things you might notice is that there is no pi over 4 on the scale. So if you think about it, if this is where 0 is and this is where pi is, let me scoot this up a little bit so you can see. So here's 0, here's pi. I know halfway between those two is my pi over 2. And halfway between these 2 points should be where pi over 4 lies. So if I take this interval and I cut it in half, pi over 4 is about right there. So when you plot the points, since you're doing a lot of rounding, obviously you're going to need to estimate where those points are. So what I'd like you to do right now is press pause. I'd like you to finish filling in the table, and then I would like you to plot the points. Okay, once you've plotted your points, this is what you should see. And what we're going to do, and it should look familiar, if you remember at the very beginning of the year, we actually looked at some graphs of sine and cosine. But now that we've got some points plotted, let's go ahead and connect them so that we can really get a good idea of what this graph looks like. There we go. This is called a sine curve. And I think the best way to describe it would be as a wave. Now, this function is unlike any of the other functions that we've seen. It looks similar to like a polynomial, for example, but like with a polynomial, if you remember, this would only be the short-run behavior. With a polynomial, the ends or the tails of the graph would extend forever in the same direction. The pattern wouldn't repeat. With a sine curve, the pattern does repeat. Think about how many times if you wind yourself around and around and around the circle, the values of y go up and then they come back down, and then they go back up and then they come back down, and then they go back up and then they come back down. And they pretty much revolve around, revolve between -1 and +1. So this pattern actually continues forever and ever and ever, indefinitely, forever, all the way to infinity. So we can actually extend this pattern. So I can see that any time, for every multiple of pi, my sine curve is going to hit the x-axis. And at every multiple of pi over 2, it's either going to be a maximum or a minimum. And so instead of plotting every single one of these points again, I'm just going to plot what I would call the 5 critical points. And so if we just sort of follow the pattern, and again, this pattern will continue forever and ever and ever. And this is a sine curve. This is what we call a periodic function. And for anybody that has taken physics, anytime you're learning about sound waves or light waves, they can all be modeled by a sine or a cosine function because they're considered periodic. And with a sine function, or with any trig function in fact, the period is basically defined by the length of time it takes for the function before it repeats itself. So for a sine function, the period, if we started here and ended here at 2 pi, I would say that the length of this curve, that would be 1 period. And for the sine function, 1 period is going to correspond to 2 pi. And that makes sense. If you think about going all the way around the unit circle, the values of y are different. And the pattern doesn't repeat until you've made 1 complete revolution around the unit circle. You might also notice that the horizontal line here, let me actually do it with a special color. Let's do it with green. So this line here, which happens in this case to be the x-axis, sort of cuts the graph in half. And that line is called our midline. And that's going to be really important because as we start doing transformations of the graph, that midline is going to shift up and down. And you might hopefully make some associations between what we're doing with the sine function and what we did at the beginning of the year with other transformations of graphs. Another important definition for us to understand is that the distance between the max and the midline, and in fact the minimum and the midline, is the same for every wave. The waves are always going to be the same height, and that height is called the amplitude. And these are important definitions when we're talking about trig functions. All right, so the amplitude is what we would define as the distance between the midline and the max, or the midline and the min. The midline obviously is the horizontal line that cuts the graph in half. And the period is basically the length of time it takes for the function to repeat itself. Now, the sine curve, because it basically is the same pattern forever and ever and ever, this graph can actually be modeled by an infinite number of equations. So if I were to look at this as, for example, y equals the sine of theta minus 2 pi, it's actually going to be the exact same graph. So there's an infinite number of equations that can actually model this function. Some important characteristics about the sine curve is that it starts, if I call this the starting spot, and ends in the middle. And it also crosses in the middle halfway. The pattern with the sine curve after it starts is it goes up to its max, and then it goes back down to its min. And so as we're drawing these graphs, it'll be important to know the shape of the sine function. And so I have another slide that also kind of shares some of this with you. So the sine always starts in the middle, it goes up, then back down, and then it ends up back at the middle. So if this is our start, this is our end, it goes up, down, and then up again. And that is the pattern of the sine function. We are only going to be looking at sine functions that have a period of 2 pi in this course. When you guys get into pre-calculus, actually you'll change the period and you'll be stretching it and compressing the graph horizontally. So you're going to be looking at really like long periods, something like this. You might also be looking at periods that look more like this. But for this course, we're just looking at periods that are equivalent to 2 pi. And in today's lesson, we're going to change the amplitude and the equation of the midline and look at just the vertical transformations of the graph. So before we do that, I'm going to actually skip over unto the definitions just to make sure that you have them down. And these are on the third page of your class notes. I'm sorry, the second page of your class notes. And so if we're just talking about, for example, the sine function, the only two transformations that we're going to be interested in today are the A and the K transformations. If you remember that from the beginning of the year, there's also an H transformation that would occur with the theta value, and we'll deal with them in another class. So A is going to correspond to our amplitude. Because remember, the A value is going to be our vertical dilation. So the amplitude would correspond to our vertical dilation, or the amplitude of our graph. An amplitude, by definition, is basically the distance from the midline to the max. Or midline to min, if you want to do it that way. Sorry, I'm running out of space. And it's always positive. And so that's important because you're actually going to see some graphs where the A value is negative. So if the A value is negative, you should remember from the beginning of the year that that means that you need to reflect the graph. And so if our sine function usually goes up, so if I'm just drawing a sine function, our parent function, our mother function, usually looks like that. But if A were negative, I would reflect this graph, and it would still start at the middle and end at the middle, but it would be a reflection of the graph. And so it would go down first and then up. The period is basically the distance it takes for the function to repeat. And for the sine of theta, the period is 2 pi. The same is going to be true for cosine. We'll take a look at that in just a minute. The midline is always going to be the horizontal line, y equals k. Oops. Okay. And this is also going to correspond to your vertical shift in the graph. If you remember from the beginning of the year, the k value scoots the graph up and down. Okay, and so the amplitude and the midline are going to be two of the shifts that we're going to do today. And so if you take a look at the next examples, basically it's asking you to identify the amplitude and the vertical shift of each function. What I'd like you to do is press pause and identify them for all of your sine functions. So go ahead and press pause now, and all I want you to do is identify the amplitude and the vertical shift, and also state whether or not the graph would be reflected. Okay, go ahead and check your answers. Notice that in number 4, even though the value of A was a -5, the amplitude itself is a +5. The negative tells me that I would actually reflect the graph. So if I were to sketch this thing, basically, I'm just going to do a quick sketch. Let's say this is my x and y axis, or my theta and y axis. With the sine function, I know I want to start with my midline. So if my midline occurs at y equals 2, then I'm going to draw a dotted line where y equals 2. I probably didn't, let me actually do this over again because I didn't make my graph big enough, sorry. Let's go like that. All right, so if I have a midline at y equals 2, I'm going to figure out where y equals 2, and I'm going to draw a horizontal line. If my amplitude is 5, that means I'm going to climb up 5 and down 5, and I'm going to mark where my max and min values occur. So my middle is at 2, so I'm going to go up 5, 1, 2, 3, 4, 5. That's my max, and I'm going to go down 5. So from my middle, I'm going to go 1, 2, 3, 4, 5. And so that's my min. So basically, my sine curve is going to just rotate back and forth between the max and the min values. I know that the graph of the sine function starts in the middle, and so I'm going to find my new y-intercept is going to still be on the midline, and it's going to end in the middle. So I'm going to label this as 2 pi. And I also know that halfway between those 2 points, it hits the middle again, and that's going to be at pi. And normally, my sine curve goes up first and then down. But since this graph is reflected, instead of going up first, I'm going to go down first. And so halfway between 0 and pi, that's going to be at pi over 2, it's got to hit its minimum. And then halfway between pi and 2 pi, it's got to hit its maximum. And so this curve is going to look like that. And it's going to go on forever and ever and ever. So you can draw little arrows just to indicate that that pattern continues. Okay, so the next thing we're going to do is take a look at cosine, and we're going to perform exactly the same thing that we just did with sine, but we're going to go back to doing cosine. So if you could scoop back, notice that you have another table of values and another graph. I'd like you to pause the recording, and I would like you to fill in the table and plot your points so that you can see what the shape of a cosine function looks like. All right, so go ahead and pause right now. Okay. What you should notice in your table is that all of the values are the same numbers that you saw with the sine function, except they occur at different places. So when you plot the points, you'll notice that your curve looks a little bit different. It's actually the same exact wave. It's just shifted a little bit. Notice that so your graph still goes, if you're looking at the beginning, so here's my beginning, here's my end. Notice that the difference before it starts to repeat is still 2 pi. And so if you remember, we call that the period. And so the cosine has the same period as the sine. Notice that the max is 1 and the min is also 1, which was also the same for the sine function. And so the curve itself is identical to the sine function, it's just been shifted over. The difference is that, remember how the sine function started in the middle and ended at the middle? Well, the cosine function starts at the max and ends at the max, and it always goes down and then back up. And this pattern continues forever and ever and ever. So for example, I know that it's also going to hit the middle at negative pi over 2. It's going to hit its minimum at negative 1. It's going to hit the middle again at negative 3 pi over 2, and its maximum at negative 2 pi. And so again, I can continue this curve or this wave pattern forever and ever and ever. And if I were to lay the sine function on top of this, if I were to like take a transparency and shift it over, they are the exact same curve. So when we're talking about modeling, any kind of wave pattern like this can be modeled with either a cosine function or a sine function. And we'll talk about that a little bit later on in the unit. But the important things to note here is that the curves are the same, so they have the same max, the same min, the same periods. We have the same midline. The amplitude means the same thing. So the amplitude, again, is the difference between the max and the midline, or the min and the midline. And the only difference really is that the cosine starts at the top and ends at the top. And so those are going to be important characteristics. When we look at, and this is just another slide, I don't think this is in your notes, but the cosine always starts at the top, it goes down and then up, and then ends at the top. But everything else about the function is the same as the sine. And so where I kind of made some comments here, for the cosine, the period is also going to be 2 pi. And the same is going to be true of the amplitude, the a value, whether we're dealing with a cosine or the sine function, it's the same behavior. If a is negative, I'm going to reflect the graph. So instead of starting at the top and ending at the top, instead of it looking like this, when I reflect it, I'm going to be starting at the bottom and ending at the bottom, and so it's going to look like that instead. And that's what the negative will do. So if you take a look at the examples, what I'd like you to do is press pause and then identify the amplitude and the vertical shift, or in this case the midline. So the vertical shift is the same thing as your midline. And then also state whether or not the graph would be reflected. So please press pause and go ahead and do those 3 problems. Okay, please check your answers. And notice again in number 6, the amplitude, or the a value in this case, is a negative 4, but the amplitude itself is still a positive 4. Your midline is going to occur at y equals 6, and that negative in front just tells you that the graph needs to be reflected. So instead of starting at the top and ending at the top, your cosine is going to start at the bottom and end at the bottom. So let's do some practice problems. And this is just, this is just another slide with some more information about your midline, your amplitude. Your amplitude is going to be considered your vertical dilation. So if you remember when we were dealing with quadratics, if we had y equals x squared, that's our parent function. And so I'm sorry, that looks terrible. So that would be my parent function. If I multiplied it by 2, if you remember, all that's going to do is stretch the graph vertically. And that's going to be the same thing that you're going to see with your sine and cosine functions. They're just going to get tall and skinny. And if the value is less than 1, then it's just going to be compressed and the graphs are going to be flat. But they'll still cross the x-axis, or the midline, I guess I should say, at the same places, because we're not going to do any horizontal shifts or dilations today. All right, so the next couple of examples actually walk you through the process of graphing, and so I'm going to do a couple with you, and then in class what I'd like you to do is work together on the rest of the problems in classwork. So the first example is a sine function. You're given that y is equal to 5 times the sine of theta minus 3. You always want to start with the midline. So go ahead, and step 1 is to write the equation of the midline. In this case, it would be y equals negative 3. And remember, if it's a y equals, it's always going to be a horizontal line. And make it dotted. If you make it solid, then it indicates that it's part of the graph. And it's really not. It's just there to help guide you as you're plotting the rest of the curve. The next thing you want to do is mark the amplitude. And so in this case, our amplitude is 5. And so from my midline, I'm going to count up 5 and down 5, and that'll indicate the max and min values of my graph. So from -3, I'm going to count up 1, 2, 3, 4, 5, and I'm going to count down 1, 2, 3, 4, 5. And so that gives me the max and the minimum values for my curve. And so the next step is to plot the new y-intercept. Remember, this is a sine function, so it starts in the middle. So it starts and ends in the middle. And so what I'm going to do, there's basically 5 critical points. And the critical points are going to occur where the graph crosses the midline and where it hits the max and the min. So with the sine function, I know that it starts in the middle and it ends in the middle. And remember, our period is 2 pi, so my ending is going to be at 2 pi. And I know with the sine function that it also crosses the middle halfway, so it's also going to cross the middle there. With the sine function, the curve goes up first, and so halfway between 0 and pi, I want to make sure my graph hits its max. And then halfway between pi and 2 pi, it's going to hit its min. And so from there, I can sketch the curve. And remember, this curve goes on and on and on forever and ever and ever. So let's just get in the habit of sketching the whole thing. So at -2 pi, I know my curve is going to be at the at the minimum. At negative pi, it's going to be back up at the middle. I'm getting all my words mixed up. -3 pi over 2, it's going to be at its max. And at -2 pi, it's going to be back down at the middle. And so if I finish this curve, it's going to look like that. And remember, these are curves. Even though we're only plotting a few points, make sure that it actually looks like a curve and not like a jagged V. Okay, and that's how you would graph the sine function. We can do the same thing with a cosine function in the next example. The first place we want to start is with the midline. So if my midline occurs at 4, I'm going to draw a dotted line where y is equal to 4. And again, it should be dotted because it's not actually part of the graph. The amplitude in this case is 3. And so that indicates my maximum and minimum values. So from the midline, I'm going to count up 3 and down 3. And that helps me identify where my max and min are going to occur. Now remember, when I start plotting my cosine, the cosine function starts at the top and ends at the top. And so when I'm at 0, that means I'm going to plot my maximum first. And then at 2 pi, I'm also going to be plotting a maximum value. Halfway between those 2 points, it's going to hit its minimum. And so at pi, it's actually going to be at its minimum value. And then halfway between 0 and pi, it's going to be at the middle. And between pi and 2 pi, it's going to be at the middle there. And so I can actually continue this pattern. And so now I can see that my curve should look like that. And if I'm going too fast, please feel free to just pause so that you can catch up. But notice that the curve itself is identical to the sine function. It's just been shifted over a little bit. The last example I want to do with you would be a reflection of the cosine. And so again, we're going to start with our midline. Our midline occurs at y equals 1. And so I'm going to draw my dotted line at y equals 1. The amplitude, remember, is always positive. My amplitude in this case is a positive 4. So from that midline, I'm going to count up 4 and down 4. That gives me my max and my min. Because the a value is negative, I know I've got to reflect my graph. And since I'm dealing with a cosine, I usually start at the top and end at the top. But because this graph has been reflected, I need to start at the bottom and end at the bottom. And remember, 2 pi is where it's going to end in terms of one full period. That means that halfway between these 2 points, that's going to occur at pi. That's my maximum. And then halfway between them is where it's going to hit the midline. And I can again continue to follow that pattern. And graph, oops, that was terrible. And graph my cosine function. There we go. Alrighty. And there's the cosine. Okay, so you have several examples that follow, and what I'd like you to do is work with the person next to you on those examples for the rest of class, and then for your homework it's just more graphing. And you'll notice that in the homework I start to prompt you by reminding you to write the equation of the midline and the amplitude and then to determine whether or not the graph is reflected, but then towards the end I take those prompts away in hopes that you can graph it by yourself. So please press pause and work with the person next to you on graphing these functions. And I will admit that the graphs are kind of small and some of them have very, very small amplitudes, and so it's a little bit hard to see. When you have fractions, it's easier to turn them into a decimal and then plot that point. But some of them are a little bit tricky to graph because the graphs themselves are a little bit small. So I apologize if that was difficult. If you press pause, when you're all done, you can press play again and I'll have the answers displayed for you. Okay, so here are the answers to the classwork. I hope that's something that you can see. Actually, let me go ahead and zoom in a little bit for you. And then I'll just scroll down. So, all right, so those are 7 and 8. And then 9 and 10. And problems 11 and 12. And I will save this video to Blackboard in case you're confused and you need to look at it again. I will go ahead and post it to Blackboard. So good luck, and we'll go over any questions you have about constraints and graphing next week when I see you. Have a good weekend.